Now for the final part of the chapter, entropy balance. We talked about entropy balance throughout the whole chapter, where I have basically been introducing the second law in its entire form, and we looked at parts of it throughout various parts of this chapter. At this point now, we're going to bring it all together and talk about how to apply a second law balance to a problem set. So again, we mentioned the second law states that entropy can be created, but it cannot be destroyed. So the increase of entropy principle can be quantified as the total entropy entering minus the total entropy leaving plus the entropy generated equals the change in entropy of a system. So here I have entropy into a system, and it transfers in by heat and by mass, minus the entropy leaving the system by mass and by heat, plus the generated entropy equals the total entropy change of a system. You can actually, by this figure, it's interesting, you can look at the comparison between a first law and a second law. First law analysis, we get the change in energy of a system equals the energy at the final state minus the energy at the initial state. Well, the change in entropy is the same basic principle. It's going to be the entropy at the final state minus the entropy at the initial state, and you can evaluate it as a property. The entropy transfer terms, entropy in and entropy out, is basically entropy transfer by heat and mass. Well, it's the same principle as energy transfer, with the exception that energy transfers by heat, mass, and work. Biggest difference between an entropy balance is that entropy can be generated. So that's what S-gen is the generated entropy, whereas E-gen does not exist. The expression that we looked at with trying to quantify the change in entropy, well, that would be called an entropy balance. And it's valid for any system undergoing any process, right? And so the statement is the entropy change of a system during a process is equal to the net entropy transfer through the system boundary and the entropy generated within the system. So let's go and let's look at each individual term of the entropy balance, starting with delta S system, right? Delta S system would be the change in entropy equals the entropy at the final state minus the entropy at the initial state. So since entropy is a property, if the state of the system does not change during the process, well, the entropy change of the system is 0. So you can evaluate that as a property, much like we have done up to this point. Now, as for the entropy transfer terms, S in and S out, well, entropy transfers by two mechanisms, by heat and by mass. Entropy transfer is recognized at the system boundary as it crosses the boundary in the same way that energy transfer is recognized at the system boundary as it crosses the boundary. So, entropy transfer by heat. Heat is a form of disorganized energy, and so the entropy transferred during this process is determined as a function of that heat transfer. So it basically would be the sum of all the heat transfer terms over its source from which it's traveling from. So work is entropy free, and no entropy is transferred by work. Energy is transferred by both heat and work, whereas entropy is transferred only by heat. So you got to remember that the entropy transferred by work is 0. And the distinction between heat and work is brought out by the second law. An energy interaction that is accompanied by entropy transfer is heat transfer, and an energy interaction that is not accompanied by entropy transfer is work. The other way by which entropy can transfer is by heat or by mass flow. Both entropy and energy are carried into or out of a system by streams of matter, and the rate of entropy transfer is proportional to the mass flow rate. So the entropy transfer by mass can be quantified by the amount of mass across the boundary multiplied by that particular mass's entropy. And then there's S-gen. Sgen is a quantity that is able to help quantify the amount of irreversibility that happens during a process. Irreversibilities cause the entropy of a system to increase. So entropy generation is a measure of the entropy created by irreversibilities during a process. So the energy change of a system equals the energy transfer for any process, whereas the entropy change of a system equals the entropy transfer only for irreversible process. And the entropy balance for any system undergoing any process is the change in entropy is equal to the entropy transfer plus Sgen, where the entropy transfer is by heat and mass. Again, this is entropy transfer by heat and mass. This is entropy generation. And this is the change in entropy of the system. It could also be written in rate form. The rate of entropy transfer to the system by heat and mass minus the rate of entropy transfer out of the system by heat and mass plus the rate of entropy generation in the system equals the rate change of entropy of the system. It follows that for reversible process, the rate of entropy generation is 0. In the special case of a closed system, there is no mass flow crossing the boundary. Therefore, there is no entropy transfer by mass. Therefore, the total entropy transfer to or from the system is the sum total of the rate of entropy transfer by heat. So the expression for the change in entropy of a closed system would simplify to the total amount of entropy transfer by heat plus the amount generated. So again, if I were to read this in words, it would be the entropy change of a closed system during a process is equal to the sum of the net entropy transferred through the system boundary by heat transfer and the entropy generated within the boundaries. In the special case too of an adiabatic closed system, this Q term would also go away, so that the change in entropy of an adiabatic closed system is just equal to the entropy generated. And finally, for control volumes, the entropy can be transferred to and from a control volume due to both heat transfer and mass flow. So the entropy transfer, the entropy balance for a control volume can be written as the sum of the entropy transfer by heat plus the sum of the entropy to the system by mass minus the sum of entropy leaving the system by mass plus the sum or plus the rate of entropy generation equals the change in entropy of the system. So in words again, this is the rate of entropy change within the control volume during a process is equal to the sum of the rate of entropy transfer through the control volume boundary by heat transfer, the net rate of entropy transfer into the control volume by mass flow, and the rate of entropy generation within the boundaries of the control volume as a result of irreversibilities. In the special control volume case of a steady flow process, the state of the control volume does not change. Therefore, the change in entropy is 0. And so that equation, the delta S portion of that equation goes to 0, right? So if I were to rewrite this, so the sum of entropy transferred by heat plus the sum entering by mass minus the sum exiting by mass plus the rate change of generation. If it's a steady flow system, well, delta S is 0, meaning that the amount of entropy generation in the system can be determined by making a balance between what's entering and exiting by mass and by heat, right? So that would basically mean that the amount of entropy generation for a steady flow system would be equal to the entropy remaining in the system due to the difference of that being transferred in and out. That would be equal to the amount that's being generated in the system.